it goes, basically the cabinet goes through and all those people.
Well, I will begin with a word of prayer. Ahem. 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 Dear Father, we thank you for this day. Again, I thank you for these students. Just ask you to bless our work today. Help us to glorify what we do and just understand a little bit more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. So let me use the projector here for a second. Then I'll put it away once I get done with my initial example or two here. So these are the harder, more nuanced properties of dot product. Of course, this feels like the right day for this. Let's see here. So, as I told my earlier class, I just lost 20 subscribers, but I gained another 40. So, yeah. All right. Anyway, so these are deeper identities for the cross product. So this we referred to as the back cab identity when I was in junior level electromagnetism, because in Griffith's electrodynamics, they put the B first and the C first, and it becomes back cab. If you need the back cab identity for something you're working out, it is particularly insidious. All right. Anyway, so if you have the cross product of the cross product, this is what happens, and it's not like if you put parentheses over here instead of over there, it's different. Like the cross product is non-associative, and this makes that somewhat explicit. There's also this Jacobi identity, which again expresses the fact that the cross product is not associative. This, in some sense, is a measure of how far from associative it is, because the sum of these is 0. Now, this right here is important to your homework, because there's a problem I ask you to find the volume of a parallel pipette, and if you use one of these formulas, it's super easy to find the volume. If you use the other two, it takes you a bunch of calculation. So I'm just saying, keep number 3 in mind as you do the homework. I was talking to somebody about this today. Anyway, I'll just say that. So this is an important thing. Notice the pattern. So like if you move A over, it goes over here, and then so forth. Now, if you don't care about the pattern, if you just write down the dot product of the cross product of 3 vectors, you can safely assume that it's going to be plus or minus what you started with. All right? I say, so like we should talk a little bit about what do we mean by right-handed triple. So like if you have 2 vectors and they're strictly, oh come on, don't do that to me, and they're strictly perpendicular, then if it's a right-handed triple, the cross product of the 2 vectors will give you a third vector which is directly perpendicular to both of them. Now, of course, that's not always possible. So the simplest idea of right-handed triple is I have like vector A, I have vector B, all right? So I take, let's say, A crossed into B, and then C goes right up. So this is sort of an example, if I can get it, come on, behave, of a right-handed triple. So A cross B goes into C. But I relax this terminology a little bit. More generally, A comma B comma C is a right-handed triple. If when you take A cross B, the third vector, it's in the general direction of the cross product. All right, so it could be anywhere up here. On the other hand, if you have A this way, B this way, to A cross B, it's up here, right? If the third vector is down here, that wouldn't be a right-handed triple. That would be a left-handed triple. All right. The most obvious example of a right-handed triple is x hat cross y hat gives you z hat. All right. X, Y, Z hat, this is a right-handed triple. And coordinate systems that are set up like that are called right-handed coordinate systems. So if you're dealing with a right-handed triple, if one of these is positive, the other 2 is also positive. And they all would measure the volume of that triple. This here is a non-trivial identity called Lagrange's identity. And this is basically, if you know that the dot product of A and B is AB cosine theta, right? Think about this. We know A dot B is AB cosine theta. If you plug that into here, what do you get? You get A squared B squared minus AB cosine theta squared, which gives you 1 minus cosine squared, also known as sine squared, and that's where this formula comes from. So like I said, it's a non-trivial identity, the fact that we can write A cross B as AB sine theta times the unit vector. My apologies for fuzziness of this projector. I'm hoping that we will soon remove the offending new technology which is not working in here and has not worked for the entire first week. So people are complaining, just not me. I trust their complaints will work. All right.
Can you keep it up a little bit longer?
This is posted, like I can, but you know, this is in the posted notes. So but. So anyway, there are additional examples in the notes, both about like projections and cross products. I'd encourage you to work through those. I haven't given you any other practice problems yet, so like in the meantime, work the notes out. That would be a very healthy thing for you to do. Some of you are already doing that. I don't cover all of the examples in class, but I think all of the examples are worth working through. So, all right, I'm gonna go on here. So this brings us to chapter 2. Which is on motion, all right? And I'm gonna skip ahead. I'll write these back out on the board here in a minute, but I just want to look at an example while I have this thing out, because I don't really want to write the example out. So this is example 2.14 here. You have let me try to see if I can make it bigger. It's kind of a, I'm told that turning the lights off is a fool's errand, so I'm not trying. Because I think, anyway, every day Dr. Dinsmore gives me some kind of like rundown on how the technology in the classroom is working. And I'm just happy that this thing is down right now, so I don't want to mess with anything, because if it comes down, then we lose a board for the rest of class. So here's the problem. Suppose you got a sailboat. It begins at the island of Cats. Then it makes a displacement of 20 miles, 20 degrees south of east. All right. Then the boat changes course to travel 30 miles at 30 degrees south of west. Finally, it travels 10 miles due north, where it reaches the island of Dogs. In what direction should the boat set sail in order to return to the dreadful island of Cats? How far is the island of Dogs from the island of Cats? Please express the direction in terms of the standard angle. All right, so what I do here is I calculate each displacement as a vector and then take the sum of the displacements to get the net displacement. There's a picture on the next page of the notes we'll look at here in a second. So first of all, south of east, right? What's that mean? So that means that you've got like, it's like this direction, right? 20 degrees. So this is east, right? This is south. 20 degrees south of east is like this, right? That's what that means. So 20 degrees south of east is this, and so if I go 20 miles at 20 degrees south, I can do the magnitude times the standard angle, cosine and sine, right? That gives me the unit vector in that direction, which ends up giving me 18.79 comma minus 6.84 miles, which kind of looks about right. So what's next? 30 miles at 30 degrees south of west. Now before I turn the page here, what does 30 degrees south of west look like? So this is west, right? So 30 degrees south of west means over here. Okay, like that. Which actually gives us a standard angle of what? What's this angle up here? That's 180 degrees, right? So 30 degrees south of west is going to correspond to a standard angle of 210 degrees for that displacement. All right. So let me go on here, and then I'm going to put this pathetic projector out of its misery. I just want to, this particular example, it helps for us to just look at it. So, all right, so like I said, we have a displacement of 200, oh man, come on. All right, I'm going to play this game here. Ha-ha. Actually, does it matter if it's up there? It doesn't matter. Same difference, isn't it? I don't know. It's a little bit more readable there. Whatever. Okay, so, sorry, it's crooked. It's probably bothering some of you. Let's see if I can fix it. All right. So 210 degrees, 30 miles. that gives us minus 25.98 in the x and minus 15 miles in the y. All right. So I have, and then finally I have 10 miles north, right? 10 miles due north. I don't need trigonometry for that. That's just 0, 10 miles. That was the final leg of the journey, right? Now, delta r is what I don't know. I don't know what it takes to finally get back to where you started, right? But I do know if you get back to where you started, then the sum of the displacements should be what? Should be 0. So we can work that out. And when I work that out, I get, delta r is minus delta r1 minus delta r2 minus delta r3, which works out to 7.19, 11.84 miles right there, right? So let me scooch this up just a bit here. So the distance, it's very aggravating. The distance is the length of that vector, right? So 13.85, we're 13.85 miles from where we started at the end of the 3 displacements, right? The 20 degrees, the 30 degrees, and then the due north displacement, right? That puts us here, a 13.85 mile trip between Dog Island and Cat Island. And so what's the angle here? Well, I can figure that out, right? It should be this angle here. I guess I can draw it. Ah, man. This angle here, right, works out to 58.73 degrees when we work out the details here. Because that's inverse tangent of like 11.84 divided by 7.19. So I wanted to look at an example with you guys because I wanted to introduce you to the terminology like south of west or south of east. We could also talk about, 20 degrees north of east. What would that look like? That'd be like, where would 20 degrees north of east be? Up here, right? So this is north of east. 20 degrees north of east. Yeah. So we can measure angles off any of the, north, south, east, west directions going either clockwise or counterclockwise, referring to the next direction, which is, the direction we're sweeping, right? So there really is, you just have to draw a picture and think through the wording, but thought I should at least spend a minute talking about that, because that sometimes gives you guys some troubles. This here, I would encourage you guys to read this example. It's a nice example. I guess I need to erase my... All right. So here I have a room with a spy mouse enters the room through a small hole in the corner. The mouse then sneaks along the wall a distance of 3.2 meters, all right, to a point B, which is as pictured. And then the mouse darts 2.5 meters over to a lamp whose base is at point C, and he climbs 35 centimeters up to the lamp here, right? And then his mission is to shine a laser at the corner A, which is 4 meters above the floor. So he's trying to shine a laser, the spy mouse, which for some reason has a laser. I don't know, imagine 20 years in the future, we've figured out how to digitize mice. So, laser. Mouse. It's hard to see, but that's the point. It's a mouse. There's a lamp here too. Use your imagination. So then the question is, what angle of inclination should the mouse set on his laser? So the angle of inclination, if I was to draw this as being like a parallel, so this line and this line down here, these are parallel. So these parallel lines, like the angle of inclination, I might call it phi, whatever. It's the angle up off the horizontal that the mouse needs to shoot the laser at, right? So like in this room, for example, for me to, let me find a better laser, a more exciting laser. So this laser, for example, you can figure out what angle of inclination do I need to shoot the laser at in order to hit the top of the board, right? So like if you go off the horizontal, looks like I got to sweep up about, 20 degrees or something. off the horizontal. Maybe I should, I don't know. So something like that. Angle of inclination up to that point, something more like 30 degrees, 90 degrees, right? Okay. So how do you figure that angle out? Well, what I did was I just figured out the coordinates of these different points with respect to a three-dimensional coordinate system, which I've drawn the origin at this corner, right? So x, y, z, a right-handed triple, right-handed coordinate system. And so like my A is, ooh, let's not use that one. It's good for pointing, but not, sorry if I shot you in the eye. But it's a low wattage laser. You probably won't lose your vision. You probably blinked. It's okay. Maybe. I did get it from China, so really who knows the actual wattage. But you guys ever watched Styropyro? Some people know. If you haven't, you're welcome. Styropyro is one of the greatest YouTube channels ever. You've seen microwaves? This man has constructed a macrowave. You want to cook a steak in 2 minutes? No, 5 seconds. It's a 20,000 watt microwave. That's just representative. He's been building like toy lasers since his childhood. It's really one of the best channels out there. Anyway, okay. So I think he's like a chemist. So this is A, which is 004. B is this point, 3200. C is that point, and D is this point. And so the delta R I'm interested in is to go from the point from the point D to the point A. We're almost done. We're going from this point D to that point A, right? So I do A minus D gives me the displacement vector from here to here, right? And then I'm trying to find the angle. So I said that the angle of inclination is complementary to the angle off the z-axis. Do you guys see that? What do I mean by complementary? Complementary angle sum to what? See, this triangle right here is a right triangle. So this angle right here is 90 degrees minus phi, right? But also, this angle right here, this is what? What's this here? This is the what? The unit vector in the z direction, right? So I can calculate that angle by taking the dot product with z hat. See, the displacement vector dot z hat gives me this, but that tells me that inverse cosine of that is 48.5 degrees. So 48.5 degrees is this angle here, which then by complementary, subtract from 90, you get 41.95 degrees is my angle of inclination over here. So this example showcases some of the things we can do with vectors in terms of finding angles between three-dimensional displacements and so forth. And anyway, so if you don't mind, I'm going to put away this miserable projector and lecture like a human for the rest of the time. So. How is it still alive? Oh, that was the HDMI. Okay. I was like, wait a minute. How did it do that? Like I thought it killed it, but it was like a zombie. It's alive. All right. Okay. Great. So I do actually like to use the projector in here a little bit, but goodness, guys, I really don't want to until things get fixed. So I don't know. I guess what I'll do as a stopgap is when I get to something that I want to project, I'll just say, please look at the notes, this, and so forth. And then as long as you guys actually look at the notes, everything will be fine, I guess. Okay, so that brings us to chapter 2, basically, which is on motion. And now some of these things I've already defined, right? So definition, the position of an object is denoted R, right, of t. This is, I should say, object at least say r, and then at time t, it's supposed to be time, we'll use r of t, right? And of course, we might have more than one position, so we like maybe r sub 1, r sub 2, so forth, all right? So n equals to 2, we usually use like r is xy. N equals to 3, what's our position look like? X, Y, Z, right? The displacement over a duration, so a duration is an interval of time, so like t2 minus t1, this would be a duration. Displacement over duration is delta r, which is r of t2 minus r of t1. So it's the difference in position vectors from time 1 to say time 2 for a given object. That would be it. It doesn't have to be for a given object. We can look at the displacement between different objects, right? It's not written in stone. You can only look at a displacement for an object. You can, like in the last example we're looking at displacements between different objects, right? It's still meaningful. Okay, so what's an event? An event is a time and a place. So if I tell you r of t, it's basically describing an event, right? Because it's a time, t, and a place, r of t. You know, it's both there. All right. So that's the start. And then the notes give you a couple of very silly examples, which I'll let you guys read, and the more interesting examples we looked at on the projector. Next up, definition. The average velocity, all right, of object with position r over time interval, say t1 to t2, is the average. And we put a clumsy average here because we almost never talk about average velocity in here. So we want to have a kind of clumsy notation that draws your attention to the fact we're talking about average, because before long, we won't talk about average velocity anymore. We'll only talk about instantaneous velocity. All right? But this is average velocity. Of course, in one dimension, what's it look like? And you know, n equals to 1. We don't need the vector, right? And we can just do like delta x over delta t, if you will. So like x of t2 minus x of t1 divided by t2 minus t1. This would be the average velocity in one dimension. But generally speaking, the average velocity is going to be a vector. All right? Now, next up, and of much greater importance, the velocity of an object with position r at time t is given by v of t, and that's going to be equal to the limit as, let's say, delta t goes to 0 of delta r over delta t. Now, if you want me to be more explicit, let me be more explicit. This is kind of a glib, somewhat. I mean, if you're trying to understand things from this limit I just wrote down, it's not the right way. If you want to be explicit. To be more explicit, what we mean by that is the limit as delta t goes to 0 of r of t plus delta t minus r of t divided by delta t, like that. So we're comparing the position at r of t with the position at, you know, t plus delta t. So if I drew a picture of this, right, your particles traveling along some path, right? And here it is at time t, and here it is at time t plus delta t, right? Well, what does delta r look like there? Like this, right? So we take the limit as the delta t goes to 0. What's the geometric significance of the velocity? What's it doing? Which direction is it pointing? So like the particle's moving in this direction, right? So which way does the velocity point? It's not a trick question. It points in the direction of motion, right? It points tangential to the path that you have. Okay? So the velocity would point just in that direction of the delta r as pictured. And I'm assuming here that the delta t is positive for the sake of my picture, but of course this limit is a double-sided limit, so, you know. Do you guys want to take limits in here? Neither do I. So let me point out that calculus tells us something wonderful. And what does the calculus tell us? How can we actually calculate that limit? Derivatives, yay, which we know how to do. You're like, but I like to take limits. You don't take the limits from me. I'm going to take those limits. Said no one ever. All right? No one says this. No one says this. Well, there exists a math professor somewhere who said this, because I badmouthed limits in a lecture once, and then I got a talking to after class because his research involves actually like using the limit as opposed to calculating derivatives of formulas. So it's a thing. But outside his experience, everyone else. So like the velocity is actually equal to the derivative of the position, right? I mean, that's what this formula means. And as it works out, it turns out that this is just dx dt, dy dt, right? Possibly dz dt, depending on if we're in, 2 dimensions or 3 dimensions, right? In 1 dimension, what's the deal? So this is 3. Fine. So in 2 dimensions and 3 dimensions, I use this notation, right? In n equals 1, though, that's a special case. Then the velocity doesn't need a vector. It's just dx dt if we're using x for that 1 dimension, right? So, all right. That's good news. Let's look at an example. I'm going to call this example 1. So suppose the position is equal to, I don't know, let's say alpha t, comma beta t squared, comma gamma t cubed. Here alpha, beta, and gamma are appropriate constants to make this dimensionally consistent. All right. So alpha probably has units of like meters per second. Beta probably has units of, say, meters per second squared. Gamma has units of meters per second cubed in order for these all to conspire to have units of meters, all right? But anyway, alpha, beta, gamma constants. And then we calculate dr dt, and what do we get? So the rule is we just differentiate component-wise, all right? So you guys know how to differentiate. Not a big deal. What we got here? Alpha, bless you, 2 beta t, and 3 gamma t squared. So this is the velocity at time t. Right, just for this, I don't do this much, but just for the sake of drawing attention to the distinction in concepts. For example 1, if we have like t1 is, 1 second and t2 is 2 seconds, and, suppose alpha equals to beta, oh, my bad, alpha is 1 meter per second, beta is 1 meters per second squared, gamma is 1 meter per second cubed, just for the sake of specificity and putting units in here for a second. Then what would r of t2 be equal to? So it's 2 seconds, so I put 2 in, I get what? I get 2. 2 squared is 4. 2 cubed is 8, and all of the units work out to meters. And then r of t1 would be 1, 1, 1, again in meters, because I made it happen, yeah? So in this situation, going from time 1 to time 2, the displacement for my example here would be r of t2 minus r of t1, which in this case would be what? Calculate the difference between these two guys. What you got? 1, 3, 7 meters. That's the displacement between these events. What's the average velocity then? Delta r over delta t, which in this case is 137 meters divided by 2 seconds minus 1 second. It's kind of silly, isn't it? So the average velocity here is 137 meters per second. So there you go. That would be the average velocity. Now, what's the instantaneous velocity? The instantaneous velocity. So you guys pick it. Do you want to look at the instantaneous velocity at the starting time or at the ending time of this displacement? Start time or end time? Student choice. End time. Very good. So velocity at time 2 seconds would do what? We put 2 seconds up into here. So we get, alpha was 1, right? So I get 1, 2 times 2 is 4. 3 times 4 is 12 meters per second. This is the velocity at time t equals to 2 seconds. As you can see, the average velocity and the instantaneous velocity, they're not equal. I don't usually say instantaneous velocity in here. It is understood that if we're talking about velocity, we're talking about instantaneous velocity. That is the logically primary idea in here. All right? Because average velocity begs many questions. Like, what's the average velocity at time 1, for instance? What's the average velocity at time 2, let's say? That begs a question, which is, well, wait a minute. Is time 2 the starting time or the ending time? And if so, over what increment, right? I always give this example, if I live 10 minutes from here, right? And, if I live 10 miles from here, and if it takes me, 10 minutes, let's say it takes me 20 minutes to get home, what's my average speed? My average speed would be 30. Oh, I just introduced the concept of speed, didn't I? Oops. My average speed would be 30 miles per hour, right? Now, if my actual velocity at a particular moment is 100 miles per hour, right, and the cop stops me, and I say, I'm sorry, sir, but I can see I'm on track to get home in 20 minutes. My house is 10 miles from school. I'm only going 30 miles an hour. The cop is not going to care that overall I'm going 30 miles an hour. The fact that at that instant I was going 100 miles per hour is going to be all he cares about, right? So instantaneous velocity is what we actually are talking about when we talk about velocity, right? Now, in practice, can you measure instantaneous velocity? You know, that's a somewhat much more sophisticated question. How do you actually measure instantaneous velocity? But in a limiting sense, we can, right? If you sample shorter and shorter and shorter times, you're getting closer and closer and closer to that concept. That's what a limit does mathematically, right? Now, of course, there's other things, other games you can play with lasers and the way lasers bounce off things and timing and all kinds of things like that, which are, beyond this course. But anyway, any questions so far? So there's another thing we should talk about, which is velocity versus speed. Velocity is a vector. Speed is not. Speed is the magnitude of the velocity. Speed is the magnitude of the velocity. All right? So we can calculate speed for our examples, right? So like for my, so what's a formula for that? So v is equal to the speed, by the way. But as a formula, v is equal to the square root of v dot v, right? Where v is the velocity. What does that look like in terms of, coordinates? Well, that's the square root of what? Dx dt squared. I'll write it three-dimensionally if you guys don't mind. I think everyone understands if we're in 2 dimensions, we just drop the z, right? So in the interest of not writing everything twice, let me just do 3 dimensions. So in 3 dimensions, that's the formula for speed. All right. What do we mean by average speed? Average speed would be the magnitude of the average velocity, that's all. All right. So speed is to velocity as distance traveled is to displacement. Distance traveled is the wrong thing to say. Distance is to displacement. So let's see here. Going back, we had a displacement. So this is the displacement. The distance between events is the magnitude of the displacement. All right? Magnitude of the displacement. And you saw me do that in the examples I projected at the start of class, right? If you go back and study those, you'll see that I did that there. So distance is the magnitude. Now that's different from distance traveled. See, distance between 2 events and the distance traveled between those events don't have to be the same thing. Distance is what I might, in sort of colloquial English, call the straight line distance, or as the crow flies distance, people will say, whatever that means. So I guess there's these things called crows, and they fly in a straight line, apparently. I mean, I've never really studied crows. Is that a legit saying? They seem to have a death wish, usually. They just sit on the road. Like, they shouldn't say play chicken. They should say play crow, in my experience. But maybe if I lived in a simpler time when people still had chickens and they were running around, it would make more sense to me. I don't know. But anyway, definition. Distance traveled by particle or object, whatever. Let's say object with position r of t over, time interval, say t1 to t2, is, we oftentimes use s for it. S is equal to the integral from t1 to t2 of v dt. Or if you like here's the formula. Dx dt squared dy dt squared dz dt squared. This is the distance traveled. You guys recognize this? What is this from calculus? Do you know? What's another name for the distance traveled? Displacement? No. Not displacement. So if suppose my object starts here at r of t1, right? And then it goes like that over here to r of t2. The distance traveled is the length of the string. If you were to drop a string along its travel path, right? Like that. The length of that string is the distance traveled. This has another name in mathematics. What is it? Arc length. Very good. This is the arc length integral. Arc length. Arc length is distance traveled. In contrast, the distance between these 2 points, right? This right here is distance. That would just be, the magnitude of r of t2 minus r of t1, right? Which is also the length of the displacement vector between the points. Distance has to be smaller than or equal to, wait a minute, does distance have to be smaller than or equal to distance traveled? I think that's true. Could you have the distance be 0 and the distance traveled not be 0? How would that happen?
You have to have some sort of distance.
Like here, how about this? Here's school. Here's home, right? So like, I'm here right now, right? Tonight, I'm going to do this. Like that, right? Later. And then probably, short of a blizzard or something silly, I'm going to then do this tomorrow. Now, I won't quite get to exactly this room, because I only teach in here Monday, Wednesday, Friday. So let's say I'll be not quite the same point, like right over here, right? Oh, wait a minute. I wanted it to be the same point again. Well, this is the wrong classroom for that. But if you could imagine, then, okay, again, tomorrow night, and then tomorrow, squared. Then I'll get back to the same point, right? In this case, the distance traveled is non-zero, but the distance is 0 between where I am now and where I am 2 days from now, right? Is this true? It's true with respect to which coordinate? It's true with respect to this coordinate system, let's say right here. Is it true in an absolute sense? Like what? I mean, it is true with respect to this coordinate system, but here I have some bad news. This is not a fixed coordinate system. This is a co-moving coordinate system with the rotating Earth, which is also rotating around the sun. The actual motion of this coordinate system with respect to the sun, or with respect to the galactic center, is really complicated. But that motion is so, we can't feel it, and for all intents and purposes, this feels like a fixed frame of reference, right? No, let me not ask if there are any flat earthers here. So like for the flat earth people, this is really a fixed frame of reference. There is none of that. All that other stuff is just a conspiracy. Someday when we have more time, I'll tell you about my alternate theory of the cylindrical Earth. I believe in a cylindrical Earth. I'll say more about that some other day. Let me finish here. Okay, so. But yes, I mean, in as much as we ignore the motion of the Earth, the distance traveled is 0, right? So with respect to this coordinate system, which is co-moving with the Earth, certainly. Anyway, so what my larger point is, if I ask a question about is the distance traveled 0, I don't expect the sarcastic, oh, it's on the Earth and the Earth's moving around the sun, so no. That's not what I'm looking for. We neglect the motion of the Earth around the sun, typically speaking. For us, we're flat earthers in physics. I guess we are. Oh no. What does this mean? All right, anyway, let me move on here. So listen, so going back to my example 1, what's the speed for example 1? The speed for example 1 is the square root of alpha squared plus 4 beta squared t squared plus 9 gamma squared t to the power 4. There you go. That is the speed for that trajectory. Yes?
Is the lower limit of the second integral still P1?
Oh no. Golly. Thank you. Yes. Very much so. So, all right, so that's the speed, right? What's the distance traveled? So the distance traveled, say from t equals to 1 to t equals to 2 in seconds, is equal to the integral from 1 to 2 of the square root of alpha squared plus 4 beta squared t squared plus 9 gamma squared t to the 4th dt. And I am going to omit some units, if that's okay with you guys, on this kind of thing. Could we do this? I ask you on the test, find a formula for the distance traveled. You may omit some units. By that I mean you have the freedom to not write 1 second and 2 seconds here. All right? And maybe if I'm feeling very, very cavalier, I'll get rid of the alpha, the beta, and the gamma, and I'll just say r is equal to t, comma t squared, comma t cubed. That's kind of how we do things in Calculus 3 for these sorts of problems. We omit units. That does make the problems look easier, so maybe I'll do that at least on one problem on the test. Okay, anyway, so any questions? Like, can I do the integral? I can't, right? But can we do integrals numerically? Yeah, sure, we could do that. All right. So what's next up? So we've got position, we've got velocity, average velocity, speed. Yep, what's next?
Why is your time to the exponent of 4 when we were talking earlier? And sorry, when you're talking about speed in the square root, you have all the different variables. Earlier, you had time to the power of 1, time to the power of 2, time to the power of 3.
Yeah.
Why is it here now it's time to the power of 0, time to the power of 2, and time to the power of 4?
Because the speed is the square root of the sums of the squares of the components of the velocity, so we square both. It's the sum of the squares of the components. To calculate the magnitude of the vector, we have to square the components and add the squares and square root them. So speed is the magnitude of the velocity. We have to add the sums of the squares of the components. That's why it's squared. So it's just that. This alpha is dx dt. Right? Alpha is dx dt, so I have to square it. dy dt is 2 beta t, so I have to square that. dz dt is 3 gamma t squared, so I have to square that. That gives me a t squared squared, which is t to the 4th. So one last thing for today is I would be remiss if I didn't tell you the final step in this story is definition. Acceleration. What's acceleration? Acceleration, A, is dv dt. So, which is, by the way, d squared r dt squared. So this is acceleration. Acceleration is the derivative of the velocity. Now, acceleration is, again, a vector. Position is a vector. Velocity is a vector. Acceleration is a vector. Now, speed is a scalar. It's the magnitude of the velocity. Distance, a scalar, the magnitude of the displacement. I don't really have a name for the magnitude of the acceleration. As far as I know, there's no common name. But it is interesting to further study the acceleration and understand how it breaks into pieces. Like part of the acceleration points in the direction of the velocity, and part of it doesn't. That's an actually interesting story that we'll have to tell a different day. But anyway, this gets us started. This is chapter 2. We'll do more next time, obviously. So thanks, guys.